Okay, any questions? So, before we delved into, before we went into the diversion of PMOS, we were doing all those things because we wanted to get a high gain amplifier. And why do we need a high gain amplifier? Because we need a high gain amplifier to realize a negative feedback loop. And why do we need a negative feedback loop? It's because we want to ensure that whatever gain, low or high, we get should be independent of any variations. Right. So, and that's how we went about doing it. And this is the structure that we were looking into before we went into the diversion. Now, so now tell me one quickly before we move, before we go about discussing this in more detail. What happens if I add a resistance RL here? What aspect of this negative feedback loop will change with the application of RL? The gain of the loop will reduce, right? So earlier the loop gain was, in order to figure out loop gain, you can break it here and same old thing. So you dot it, you apply V test. So in the absence of RL, this voltage would have been what? V test times GM times R0 parallel KR. Negative. Okay. So your loop gain would have been GM times R0 parallel KR. And as long as you can keep this much greater than 1, as long as you can keep this much greater than 1, in the closed loop scenario, by closed loop scenario, I mean, when you have not broken the loop and you have applied the input, this V0 would have been approximately equal to what? K times V. Because ultimately these two nodes will track each other, right? These two nodes will track each other. If that is Vi, this will also be Vi. If this is Vi, V0 will be K times Vi. Now, after application of RL, what aspect of the loop changed? Let's concentrate on the figure on the left. Loop gain would have changed, right? So essentially your loop gain would have been, help me out, what will be GM times? Yeah, R0 parallel KR parallel RL. Now, if we can make this, again, this is a if we can make this greater than 1, much greater than 1, what would V0 be? In the circuit in the diagram on the right. So if it would be same, right? V0 will be K times Vi. Right? So what does this imply? I mean, okay, so let me be more specific with the question. So, so what does this imply? How does the output get affected with the application of a load RL? Right, exactly, right. As long as you can keep the loop gain high enough, then V0 is independent of RL. Right? That's what it means. And this is what we are after from the beginning of this course. Right? So essentially what we are making an amplifier, and a good amplifier should be independent of what it is driving. If you need to make a good amplifier, you have to, I mean, by definition, a good amplifier should have high gain or should have some gain, but more importantly, that gain should be independent of what it is driving. good voltage control voltage source, if we have to be even more specific. Okay, and that is possible in this case because you have negative feedback. Because the negative feedback works with the principle that it has to track the error and drive the error towards zero, regardless of what you have connected anywhere in the network. And wherever you have injected any disturbance, it doesn't really matter. The only thing that is sacrosanct is the input to the error amplifier should tend to zero. If you can ensure that, then you get what you want. Okay, does that make sense? Okay, fine. So now we can look at this same thing from another angle, from the perspective of output impedances, right? If you have a voltage controlled voltage source, its output impedance should be low, high, what? Low, should be low. So does that mean this contraption that we see and we find out R out, it is approximately equal to how much? It will be approximately equal to 1 over GM, right? And why? Not actually 1 over GM, but of that order. So we can also let's look at it. So if you have to find out the output impedance, we do the same old thing, V test, and we try to find out I test. If this is V test, what will be this feedback voltage? This will be V test by K. So what will be this current that it will draw in? GM times V test by K, right? And if we ignore R out for the time being, let's say R out is infinity, right? If we ignore R out, so what is now V test over I test? So this is I test, right? This becomes I test. Approximately. I mean, one can always argue that there is a current that is going through this. So there will be an additional term, right? So if you have to be more rigorous, you can say that I test equal to GM V test by K plus V test by KR. Right. So essentially your R out becomes KR parallel K by GM. And by design, you have ensured that GM times R is much greater than 1, right? GM times KR is much greater than 1. So this is approximately equal to K by GM, right? So using negative feedback, you have been able to you have been able to reduce the output impedance of this network. It's not of the order of R, it's not of the order of R out, it's of the order of 1 over GM or K over GM in this case. Okay, so which means that this can potentially look like a very good voltage source, as long as you can ensure that this R out is much lesser than RL. So to make a good okay. So now the good thing about this VCVS is that you can also get a gain of more than 1. You are getting a gain of K. So the source forward architecture that we had done earlier, you were limited by the gain. The gain was less than 1, at max 1. In this case, you can get gains of more than 1. Not only that, you can also make the output impedance low. And not only that, you can also make the output impedance independent of RL. I mean, the last two statements are related, but just to make things sufficiently clear, a VCVS is supposed to be driving an output in such a way that the output is independent of what it is driving, which means that you have to make the output impedance of the VCVS much smaller than whatever it is driving. And this architecture in negative feedback is able to do that. And how is it doing that? If you look at the output, if you analyze this contraption from the perspective of output impedance, you apply something at the output, right? You excite the output voltage. That part of that output voltage comes and kicks the error amplifier through the feedback network, and it kicks in a direction that it draws in large amount of current from the output, and that's how it reduces the output impedance. And without negative feedback, this wouldn't have been possible. Okay, does that make sense? Okay, so do you see the signal flow? So any excitation over here gets to the input, or the part of it gets to the input, and that creates the current. And this is the main part of the loop. Everything else are bells and whistles, right? They are secondary things. You have resistances, parasitic resistances, and everything. Those are something that comes along with the loop, but that's not the main component. The main component is the excitation at the output goes and kicks the input. Okay. And now coming back to our discussion of the MOSFET, we wanted that PMOSFET. We wanted that PMOSFET because we wanted to ensure that this error amplifier is strong enough to kick the loop in the right direction. By kicking means, in this case, you need high gain. Okay, and if you need high gain without using a large power supply, which means you need some active load, right? Because ultimately the impedance of a transistor looking into the drain is large, so we wanted to leverage that. And since this GM, whatever I am drawing as a symbol, transistors, yeah, right. So this symbol, what we have been doing till now was and if we take the output from here, so this was our, and for this particular case, this, let me name this, right? Yeah, this is already named, right? This is V0. This was the V0. Now, if M1 and M2 are identical and they both have identical GMs, so what was V0 over V1 minus V2? That is V0 over VE. Let's say this is GM. GM by 2 times RD, right? And this was happening because we analyze this using superposition. You assume V1 to be there in the absence of V2, and then you find out this current. Incremental current was GM by 2 times V1. And then you do the other thing. This current becomes GM by 2 times V2. And the effective current that flows to the output node is GM by 2 times V1 minus V2. That flows into RD. So you get GM by 2 times RD. Okay. So now that, this expression is basically the expression of a common source amplifier obtained from a different circuit. So all the problems of the common source amplifier naturally translate to a diff pair. Now, in the last couple of classes, we figured how to improve the gain of a common source amplifier without increasing the power supply. And that is the same thing we can do in this case also, right? So help me out. What should we do? What is the only major change that we need to do? Yeah, replace RD with a PMOS. Looking into, so that I look into the drain, right? This side should be a drain. So let's do that. And we have to bias it. So let's bias with this using the same contraptions that we used earlier. So what is the quiescent? So let me mark everything properly. So let's say this is V1 plus V1. This is V2. So okay. So let's assume the biasing is identical in both cases, because that's how the feedback loop will ensure the quiescent points to be. So this becomes, let's say, PCM plus VCM plus. By CM, I mean common mode. That is one of the standard definitions. It's a common voltage between both terminals of the DFAM. So it's called common mode voltage. So we call it PCM. So now what is the current that is flowing through M1 or M2? Biasing current, quiescent current. I0 by 2 and I0 by 2. So in order to balance, say, let me call this M3, M4. In order to, let's say M3 and M4 are also identical. That is 1:1 mirroring ratio. So if we have to ensure that I0 by 2 flows through M4 also, what should be this current source, sink value? It should be I0 by 2. Great. So now what happens when I have applied incremental inputs V1 and V2? What is the total current through M1 then? So this was I0 by 2, and after applying, let me call V1 minus V2 to be equal to delta V. So what will be the total current through M1? Right. So this plus GM by 2 times delta V. What will be the total current through M2? I0 by 2 minus GM by 2 times delta V. What is the total current coming from top? It's I0 by 2. Total current from top doesn't change. It's I0 by 2. So you have some extra current, right? So what will that extra current do? Where will it flow? Let's assume the loop is not there right now. So we are only trying to figure out you are right, it will essentially flow in the loop if the loop is completed, right? But if we want to analyze this open loop differential amplifier to see whether open loop differential amplifier gives me a high gain, right? So then we can put it back in the loop. So our motive here is to figure out, can we get high gain from this open loop structure? Okay, so where will this extra GM by 2 times delta V flow? It will flow into the parasitic capacitor, and that's true. And now let me add another addendum to this. So assume you have channel length modulation. So you have RDS at the output, right? Some are not at the output. So where will this delta V flow, this extra current flow? Into that resistor, right? Into that parasitic resistance. And what is the parasitic resistance? We also derived this. What is the output impedance of the DFAM? So the output impedance of this structure was 2 RDS 1 parallel whatever was connected to the top. In this case, what's connected to the top? What is the impedance looking up? No, why it's 1 by GM? It's RDS of M4, right? So this was 2 RDS 1 parallel RDS of 4. So let's call this R out. So where will this extra GM by 2 times delta V flow? It will flow into that R out. It's a small signal current. It will flow into the small signal impedance. So you will get an output V0, which is equal to what? Tell me. GM by 2 delta V times R out. And in this case, your V0 over delta V, which is essentially the gain, is GM by 2 times allowed. Okay. No, it won't be, right? So it's basically the same thing as this structure. Just that we have replaced the RD with the PMOS. So current is still GM by 2 delta V. Isn't it? So the same thing you can, this is a one-stop way of analyzing. You can also Nortonize it and do, right? We did the Norton equivalent of this. The Norton equivalent of this was the short circuit current was GM by 2 times delta V. The output impedance was whatever, 2 RDS1 parallel RDS4. And this is your output. In the absence of any load, your output V0 would have been GM by 2 times delta V times R. So you can either do the Norton equivalent, or you can directly write the output expression looking into the network. Okay. Does that make sense? Okay, so now what I mean, the thing that from the quiescent point, from the quiescent perspective, you see we are using 2 current sources, right? Just like you cannot use you should not. It's not very useful to use multiple voltage sources. You should derive all the voltage differences from a given voltage source. Similarly, you should ideally avoid using multiple current sources. So you'll be given one current source, right? And you should be able to get all the currents from the single current source. And we know how to get this, right? We can mirror it. We have done current mirrors extensively. We can mirror this one. So I'm not showing the bottom current source how you will get. But what about the current source on the top, which gets you I0 by 2? We can also get that, but looking into this circuit, can you, complete your thought? So looking into the circuit, do you see a branch from which I can extract that I0 by 2? The left branch, right? So this branch here has a quiescent of I0 by 2. Right? So why waste? Anyway, that current is flowing I0 by 2, just mirror it from there. You need not have another current source. Isn't it? So what happens if we do that? Something very interesting happens. So this has to be biased. Yeah, let me come back to this again. So you had this, right? So this was I0 by 2. This was getting mirrored to the MOSFET on the right. But this, we notice that this current is also I0 by 2. Okay. And since this is connected to the drain of M1, it will be unaffected as long as we keep M1 to be in saturation. Okay. So what we can do, we can simply say that we will mirror this current into here and get rid of this. Right? So we can do that. So I didn't understand the question. Can you repeat? So M3, M4. Yeah, now tell me, what was the question?
Sir, why we are trying to mirror it? I not by quality, it will be any kind of.
This is I naught by 2.
Yes.
And that is I naught by 2. Right? So we are wasting current, right?
We can remove.
Yeah, we can remove this and take the current from the left branch. That branch is anyway not doing anything, just sitting and giving bias. Right? So that's the thought process. So we can do that. So basically remove the mirroring part here. This current is I naught by 2. If this is I naught by 2, this is also I naught by 2. Okay. So this is as far as the biasing picture is concerned. No change in biasing. Whatever was happening earlier, same thing is happening right now. Just that we have extracted the bias current from somewhere else. Okay. Correct. So firstly, one reason you will see in a couple of minutes, but even if you consider from the perspective of power consumption, so what was the power consumption of this circuit? So you are having I naught, basically you have 3 branches of I naught by 2 now, right? So your power consumption is I naught by 2 times 3 times VDD. So in this case, what is your power consumption? So you have reduced the power consumption.
Even in the top.
Right.
Even there, if we remove the mid branch, then also I not by 2 and I not by 2.
Okay, you're saying if I remove this, okay. So you're saying if you remove this completely. Okay, so how will you ensure I naught by 2 flows through M4?
It will bias the M4.
How?
Again with the current.
Oh yeah, either you have to use a voltage source or you use a current source. I don't want to use a voltage source, which means you need a current source. So now let's apply an input, right? In the sense that we apply V1 and V2. So apply V1 and V2. So what is, again, let's do the same thing. What is this current? I naught by 2 plus GM1 delta V by 2. Correct? What is this current? I naught by 2 minus GM1 by 2 delta V. What is the current flowing through M3? What is the current flowing through M3 now? Quiescent is I naught by 2. It will increase, right? The current through M3 and M1 are same. So if M1 has I naught by 2 plus GM1 times delta V by 2, the M3 should also have the same thing, correct? So this will also be plus GM1 by 2 delta V. Can you repeat again? Correct. Right. So since M1 and M2 are identical, they have been, the current of I naught is flowing identically, is splitting identically between those two. If M1 and M2 are not identical, it will not split identically. Yes. I didn't understand. Right. Which circuit are you talking about? This one? I didn't understand the question, but I hope your doubt is clear. Okay, so if I naught by 2 plus GM1 by 2 times delta V flows through M3, how much will flow through M4? Same, right? So earlier, see, earlier I naught by 2 was constant I naught by 2. Sorry, earlier current through M4 was constant I naught by 2. Now it will be I naught by 2 plus GM1 by 2 times delta V. Right? Just mirroring effect from left to right. So now what is the I mean, let's do the short circuit current first. Let's do the short circuit current first. So let's assume we are doing incremental short circuit. So what is the short circuit current that is flowing into this node? GM1 by 2 times delta V minus of GM1 by 2 times delta V. So this becomes GM1 times delta V. This is an incremental short. Yes. So what was the short circuit current in the earlier contraption where we didn't have the mirror on the top? GM1 by 2 times delta V, right? Just by adding a mirror, you have been able to double the short circuit current. So that's good, right? Because ultimately we want as high as GM as possible, but as high and R out as possible. Okay, make sense? So our new contraption is this. This is as far as the ISC is concerned. Now I also have to go back and see whether it has any implication on the R out. Because there has a mirror. I mean, now the left branch and the right branch are talking to each other through an additional mirror. So we'll have to go back and see whether that has an implication on finding on the expression of R out. Okay. So let's see. So incrementally, if we have to figure out what is R out. Again, this is the incremental test voltage. I mean, we have stopped replacing transistors with symbols of control sources. I'm assuming all of you are comfortable now. Okay, so now if you apply V test, it will draw an incremental current of I test. And it has two ways to go, one on top, one on the bottom, right? So here, it will, let me call it this one I1, this one I2. And obviously we have these. So the principle that we will follow is if there is a current division between 1 over GM and RDS, we'll assume that the entire current goes towards 1 over GM, right? And if it's a competition between RDS and infinity, then obviously the current will go into RDS and not into infinity, right? So these are the two things we'll follow, and we'll try to see whether it has any implications on the output impedance from the last time when we did this. So let's do the thing that we have done earlier, right? Let's try to figure out what is I1, that is impedance looking down, right? I1 by V test will be the impedance looking down. Let's try to figure out what is this impedance. So this we have already done, so this should be quick. So what do you think? How will we proceed? We are looking into the drain of M2, but the source of M2 is not grounded. So you need to figure out what is connected to the source of M2 in terms of impedance. So what is the impedance looking at this side? Yeah, can you speak louder? RDS1? I cannot hear. Can you be louder? No. Why? Looking into the source, right? I'm looking into this side. The expression that you're talking about is looking into the drain of a transistor when something is connected to the source. Yeah, but you need to figure out what is connected to the source of first, right? In order to figure out what will you multiply with, right? I mean, essentially what you are saying is that if I know what is connected here, then looking from top, I know the expression. Correct. But what about the second? This R is not RDS1. Why? Approximately 1 over GM, right? And yeah, and if we have to, if I sent out a sheet yesterday, did you guys get it? Yeah. So if you find out exactly what it is, this will become RDS1 plus what? Yeah, definitely we will get. No doubt, but it will consume more time, right? It's again table. You can do 6 plus 6 plus 6 plus 6, or you can just say 6 times 4 is 24. Okay, fine. Do the small signal model and tell me. What is the, I mean, if you have to find out the exact expression you need, whatever is connect, what is the impedance looking up from here? Right? So impedance looking up from there is RDS3 parallel 1 over GM3, which is approximately 1 over GM3. Right? So now you can tell me. 1 over GM. Is that correct? Okay, yeah, fine. So whatever, now once you do that, then if you use that principle of, is it recording? Okay, so now if you use the principle that, or if the current has to divert between 1 over GM and RDS, we'll assume that all the current flows into 1 over GM. So what is the impedance looking into the source of M1 then? Approximately 1 over GM1. So now we have, now you can say that looking into the drain of M2, this is what it looks like. Looking from top is approximately impedance is RDS1 plus 1 over GM1 plus GM1 times RDS1 times 1 over GM1, which is 2 RDS1. Right? So this is the thing that we did earlier. So this should not be of any surprise that impedance looking from top is 2 RDS1. But the more interesting thing happens about the impedance looking up. Right? So what do you think is the impedance looking up if you don't do too much analysis? RDS4, right? So that definitely will be a part. But note that, note a very important thing. This I1, this incremental I1 is flowing through this. And when it flows through this, it excites the gate of M4. It excites the gate of M3, thereby exciting the gate of M4. Or in other words, M3 and M4 are mirrors. Right? So there will be a current I1, which will be flowing also because of this mirroring effect. Correct? So the current going on top, right? Current going on top is not only the current going into RDS4, it will be also the current due to the GM effect of M4. Correct? So essentially, what is I2 now? So let me sketch it in such a way that I2 is the combined current. So I2 is essentially V test over RDS4, which is obvious one, plus I1. Correct? So this is I1. And what is I1? I1 is the one that we figured out moments back, right? V test by two RDS. Okay. Is this clear or it's confusing? Not clear? Okay. Yes. You are looking into, okay, correct. Yeah, it should be RDS2, right? Yes, you are right. This is RDS2. Yeah, that I agree. Okay, so let's go over what is happening once again. So are you comfortable with this impedance looking down? This is RDS2. Are you comfortable with that? If you're comfortable with that, rest is basically just following the current. So if that is RDS2, what is I1? We'll go there. You mean this? You mean in this expression? Looking into the source of M1? Yeah, so you're looking into the source of M1. That is approximately equal to 1 over G. You have other terms, but that is a dominant term. Yeah, so they will go off, right? Almost. So that is approximately 1 over GM1. So you just pick the winner and go ahead with it. So let's follow the just follow the current, right? So what is I1? If I know the impedance looking down is 2 RDS2, so I1 is V test by 2 RDS2. Okay, so where will this I1 flow? This I1 is flowing out from here, which means I1 will flow into this. Correct? If that I1 flows out, it has to go here. If it goes into that box, it has to come out of that box on top. So if that becomes I1, that goes into M3. M3 and M4 are mirrors, right? So M3 and M4 are mirrors. So in other words, if you are not comfortable thinking about mirrors that way, you can say that this I1 that flows in produces an incremental voltage at M3. Correct? So what will be that incremental voltage approximately? The gate of M3, yes.
Gate is common in the grounded.
Correct. And it's connected to the drain and gate. Drain and gate are connected. So this is, what is the impedance of this transistor looking into M3? Right. So impedance looking into the drain of M3 in this case will be 1 over GM3 because it's diode connected on the PMOS side. Correct. So this voltage will be I1 by GM3. Correct. If that is, I mean, obviously I'm neglecting the current due to RDS. Otherwise, it will be parallel RDS3 and all those things, right? So if this is the case, what will be the current? Now the gate of M3 and M4 are shared. So the gate of M4 is getting excited with I1 by GM3, right? So what will be the current through M4 because of this? Yeah, so you'll have GM4 times I1 by GM3, and since all GM3 and GM4 are identical, in other words, 1:1 mirroring ratio, the current will be I1, right? So this current that will flow through M4 will be I1. Correct? Does that reduce the confusion? Okay, fine. If that is the case, what is the total I2? Total I2 is I1 plus V test by RDS4, right? V test by RDS4 is the obvious one that will always come. So your total I2 becomes V test by RDS4 plus V test by 2 RDS2. So what is I test now? I test is I1 plus I2. Correct? I test is I1 plus I2, which means I1 was V test by 2 RDS2 and I2 is V test by so this is equivalent to okay, what is I2? By definition, the direction we have marked is the current going into the drain of M4. So now, in the current going into the drain of M4, obviously has I1 included because of the mirroring. Extra is the current through RDS4. Yes. Question? Yeah, exactly. It's 2I1 plus current. Exactly, that is what it is, right? So, I mean, I2 includes I1, one term of I1, right? So, because one term goes down, a part of the current that goes down also comes back from top in the other direction because of the mirror, right? So, that's what is causing this. So, this RDS2 plus RDS4 effective, I mean, 1 over RDS2 plus 1 over RDS4 is behaving like a parallel combination of RDS2 and RDS4. Right? This looks like you have parallel combination of RDS2 and RDS4. And if we look at the circuit now, this will kind of become quite obvious. So if we look into this node, you see it's connected to two transistors M2 and M4. Correct? So this almost behaves like there is no feedback, I mean, no double path and all those things, just like we have one transistors RDS4, another transistors RDS2 connected, and you are looking from here. Right? This expression essentially looks like that. And that's how it's easy to remember also. But you should understand that this doesn't come because of this effect. This parallel combination of RDS2 parallel RDS4 comes because there are multiple effects, right? You have mirroring, and because of the mirroring, current gets doubled and so on and so forth. Okay. Yes. Yeah, if you can come up with the same thing without doing an approximation, you'll end up with a page-long term. But if you keep on neglecting the higher order terms, or rather, in this case, non-dominant terms, so you'll end up with the same thing. Yes. But you have so many RDSs, so many GMs, right? So each one of them will come up in the expression and will take equal weightage as far as the space is concerned. Yes, right. Obviously, I mean, as far as the mirror is concerned, it doesn't know whether it is mirroring a changing current or a constant current, right? So they will always be. Yes. And if you are if you don't want to do that, you replace it with a small signal equivalent and see whether the gate is getting excited. If the gate is getting excited, it will obviously translate to the current is getting excited in the mirrored branch, right? Okay, fine. Let's stop here. Thank you.